Hi there, everybody. It's me, Susan Sakya, and today I'm about to present the virtual lab experiment on designing and stimulating the various code converters. These are my table of contents. And my main abstract is that the code is a symbolic representation of data information. And here, I'm including the code conversion of binary coded decimal, gray, and access tree from one to another and in version 2. This virtual experiment is carried out using the simulator provided by MHRD Government of India initiative, whose link I have provided here. These are the keywords and full forms. BCD, ASCII means American Standard Code for Information Interchange, as we all know. And then MSB, the most significant bit, gray, access tree. The experiment I'm about to explain here, its aim is to design and simulate binary to gray, gray to binary, BCD to access tree, and its inversion. Before this, we all need to know about the knowledge of the basic number system. The objective is to understand different codes, simulate it, and to understand the importance of code converters in our real application life. So the apparatus required here is NAND IC 7400, NOR IC 7402, NOT IC 7404, and IC 7408, OR IC 7432, and XOR IC 7486. So let's move into theory. We all are familiar about the binary codes. It is of base 2 of symbols 0 and 1. And here, each bit carries a weight based on its position relative to the binary point. And the weight of each bit position is 1 power of 2 greater than the weight of the position to its immediate right. Similarly, BCD codes is the numeric codes used to represent the decimal digits like 0 to 9. Each has its own binary code, and it's necessary to use a sequence of at least 4 digital binary bits. Such a sequence of binary digits which represent a decimal digit is called code word. Now what we are unfamiliar is gray codes and access tree codes. So let's start with the gray codes. Now this is the non-weighted code not suitable for arithmetic operations. So it's not so applicable us in our physics, theoretical physics. So here I'm about to convert these gray and access codes to binary and vice versa. So gray codes is a cyclic code because successive code words in this code differ in one bit position only. That is, it is a unit distance code. Its application is in the instrumentation and data acquisition system where linear and angular displacement is measured. Similarly, it's used in SAFT encoders, input-output devices, AD converters, and other peripheral equipments. Another code is access tree code. This is also a non-weighted code, but here the access tree code for the decimal number is performed in same manner as BCD, except that the decimal number 3 is added to each decimal unit before encoding it to binary. Suppose we have the decimal 2, right? Now its binary is what, like 0, 0, 0, 0, 1, 0. Now in terms of access tree code, we have to add plus 3. That gives me 5. and the corresponding binary number of the 5 is exactly the access tree code. Here, the most important gate that we need is the XOR gate, denoted by the symbol A direct sum B, whose output is low when the both input are same. Now, we start with the code converters. Now, as we all know, the code converter is a circuit that makes the two system compatible even though each uses the different code. Now here I'm about to explain the 4 types, starting with the binary to gray code. Now, to convert from binary to gray, now let's suppose the gray codes are denoted as Z3, Z2, Z1, Z0, and binary as DCBA. Now Z3 here is equals to D itself, but Z2 equals D direct sum C, Z1 equals C direct sum B, and Z0 equals B direct sum A. This is this truth table. And this one's its logic diagram. We will check in the simulator. First, let me complete the theory. Another one is gray to binary. Here also D equals Z3 and C equals Z3 direct sum Z2. But here B equals Z3 direct sum Z2 direct sum Z1 and A equals the direct sum of Z3 direct sum Z2 and Z1 direct sum Z0. A and B are the some modification it's made than the previous one. And this is a truth table. And this is this logic gate diagram. The third one here is binary coded decimal to access tree. Here, our equation would be like if WXYZ is the access tree code and BCD, binary coded decimal are ABCD, then Z equals D bar, Y equals CD plus C bar D bar, and X equals B bar C plus B bar D plus B C bar D bar, which can be modified by taking B bar common from first and second terms, which would lead me to B bar times C plus D plus B C bar D bar, and W equals A plus BC plus BD. This is a truth table, and this is its logic diagram. And the last but not the least, access tree to BCD. This is a truth table, and this one's logic diagram of it. Now here comes the procedure. So starting with the appropriate code converter from the tab menu, we execute the simulation by pressing the run button and observe the outputs of code converters on the output LED. And we repeat the procedure for different inputs and note down the corresponding outputs. And let's check whether the truth table verifies it or not. So I'm going to take you to the simulator where the virtual lab experiment I did. Now let's check, starting from binary to gray. Now let's check the anyone, like I'm choosing the second one, right? Here, B naught is 1, so I'm keeping B naught 1. Now our output should be 0, 0, 0, and 1. So let's run it. And we got the same result, 0, 0, 0, 1. This is how we did it. Similarly, gray to binary. Let's take any. Now I'm keeping this fourth one, where the Z1 and Z0 inputs are high and other are low. Let's run it. Now this corresponding binary of the given gray code is 0010. And does it match? Yep, 0010. Similarly, third one, binary coded decimal to access. Let's run any. Like I'm running this last one, 1001. So B3 100 and 1. Our answer should be 1100 in the access3 code, right? So let's run it, and 1100. And the last one, I'm taking the second last, 1011. So 1011, and I'm running it, the program. Then its corresponding binary coded decimal is 1000, which is correct with the truth table. Then here are some of the screenshots of it. Now this I did virtually. For the theoretical calculation, I've taken some screenshots and I'll try best to describe it. For the first one, let's convert binary to gray code. Now I have the binary number 101011. Now this first one is the most significant bit. So we write this one as it is in gray bit 2, gray code 2. Now for same we write 0, and for different we write 1. So let's match this 2. Now 1 and 0 are different, right? So answer should be 1. This one's 1. Similarly, 0 1 different, so 1. 1 0 different, so 1. 0 1 different, so 1. And 1 1 same, so 0. So it's easy. So the corresponding gray code of the binary code 101011 is 111110. Let's move on to second. Now it's inversion from gray code to binary. Given gray code is 110010. Now here, most significant bit first one we write as it is, like we did in the previous, but here we compare the result and the second one of the given inputs. So this 1 and 1 is same, gives me 0, 0 0 same, 0 0 0 same, 0 0 1 is different, so 1, and 1 0 is different too, so it's 1. Its corresponding binary bit is 100011. Now converting binary coded decimal to access3, this one's a little tricky. So write the binary coded decimal and label it from the last and put and choose from last up to 4 bits. And if it isn't enough, then you have to add 0 in front. Like here in 0111, here 110 has only 3 bits, so we added 0 here. Now its corresponding decimal bit we have to find out. As we all know from the formula, like 8421, here 0 means, now that's 0, right? And 1 means 4. 4 plus 2, 6, and 6 plus 1, 7. Now this binary is equivalent to decimal 7. Similarly here, 8, that's 0, and that's 4, 1, so we can take 4, and then again 1, so 4 plus 2, 6, and 1 is 0, so 0. That would give me 6. 4 plus 2, 6. Now in access3, what we have to do is here just simply add 3 to each bit. Now this becomes 9 and this becomes 10, right? And generally we don't write it 10, we write it as A actually. And this corresponding binary bits of 9 is 1001 and A is 1010. Combining it, we get the final answer of converting it finally to access tree from BCD. And the last one, from access tree to BCD, now that's inversion. Here, all we gotta do is the same process, but here, instead of addition, we do the subtraction. Like this one's decimal is 6 and this one's 7. Now in previous we did addition, now here we subtract it. Now this becomes 3 and that becomes 4, and its corresponding binary digits we combine and we get the binary coded decimal. And I finally completed it. So in the conclusion, all I did was converting binary to gray and BCD to access tree and vice versa. I also simulated and its truth table is verified. I would like to appreciate the constant effort made by Dean, HOD, and all faculty teachers to encourage students for the virtual lab work. And also I would like to thank MOE Government of India initiative for making this virtual lab possible. Here are some references which I got this information from. And here they have in appendix, I have written some objective questions and try to solve it. And these are the answers. Like first one here, the decimal number of 6 in access tree is written as like we add 6 plus 3, which gives us 9, and this equivalent binary is obviously 1001. So this is the answer. Similarly, this one's a definition type. Like if each successive code differs its preceding code by a single bit only, then this code is called obviously gray code. And gray code of binary 0000 is the same. It's because like writing the MSB 0 as it is and adding and 0 are same. So we write the other results also 0 as, and we get 0000. Similarly, the decimal number 279 will be represented in access tree code as like in 2, 7, and 9. We gotta convert it to binary first and then add 3. But here, in place of adding 3 in decimal numbers like plus 3, we first convert this one 279 to respective binary, and then we add 3 in binary. So 3 in binary is actually 0011. So when we add it and we get the answer, this C1, that's 010110111100. And finally, the last question, the binary code of the gray code 1000 is like MSP. First one we write as it is, and then this 1 plus this 1 and this 0, it's different. So we write 1 and then again 1, 0 different. So 1 and up to end, we have all the high bits. So the answer is 1111. Thank you for listening till the end.